Hello, my name is Benjamin Murdoch. Welcome to my presentation for my final project for time series and forecasting. The dataset I will be analysing contains the monthly price of iron ore globally. Iron ore is one of Australia's biggest exports, and the sheer amount distributed is only increasing. In 2020, Australia exported over 867 million tonnes of iron ore, which was 31 million tonnes higher than in 2019. Because of this, the Australian economy is hugely dependent on its value, and so is the value of the Australian dollar. This is why it's important for economists in Australia and globally to track and be able to accurately predict the value of iron ore and prepare accordingly. The monthly value of iron ore globally between January 1990 and August 2021 is shown here. The units are measured in US dollar per metric tonne. Clearly here one can see that the data prior to 2009 is far less detailed than after, and so I chose to trim the data set from January 2009 to August 2021. There also appears to be a change point around this time, so predictions based on the data prior to 2009 would probably not be accurate. For the trimmed series, I believe there does not appear to be a trend in either direction. There is no clear seasonality in the data set as the fluctuations are sporadic, although there is certainly changing variance in the time series as said fluctuations are absolutely varying in size. As for behaviour, the model appears to have elements of moving average tendencies, but also successive points, leading one to think that there are also autoregressive tendencies. The possible change point at the end of the data might complicate the modelling process. When assessing for trend models, it is clear that the time series is not linear, and so I used quadratic, cubic, and seasonal models and found that my best combination was either a cubic model or a cubic and seasonal model combination. And although the cubic and seasonal model achieved an R-squared value of 0.895, I am more interested in using ARIMA modelling techniques for this time series, that being because I think the autoregressive and moving average tendencies will provide a strong ARIMA model. When testing for stationarity, I found that the raw data is not normal, but the first lag is. From this, I did a series of tests on the first difference of the iron ore dataset and was able to come up with 11 potential ARIMA models for forecasting on the iron ore dataset. From the ACF and PACF plots, I found ARIMA 111 and ARIMA 112. From the EACF plot, I found ARIMA 011, ARIMA 012, ARIMA 210, ARIMA 310, and ARIMA 212. From the BIC table, I found ARIMA 013, ARIMA 113, and ARIMA 313. I found that ARIMA 213 was not possible for this dataset in the parameter estimation phase, and I had to remove it. I created a model for all of the ARIMA models mentioned in the prior section. When I ranked the AIC and BIC values of each table, I found that ARIMA 011 was clearly the best model, as it was the best achieving model in terms of AIC and BIC. The summary statistics of my chosen model are displayed in the synopsis in the middle. The model has a mean error of 0.35, a mean absolute error of 7.28, and a mean absolute squared error of 0.23. The coefficient test at the bottom is included to display that the coefficient for the moving average is very significant. This step is more important when there are more coefficients in the case of any overfitting. However, it is useful to still know that the coefficient's p-value is extremely low. Moving on to residual analysis, we notice that the Shapiro-Wilk normality test deems the residuals as not being normal. This is obviously a clear issue when using ARIMA to forecast. When I look at the residual plots, however, I can see clearly that there is an outlier in the data, that outlier being the final point in the time series dataset. When visually analysing the histogram and residual plot, I can see that the rest of the data is well within the 3 standard deviations each way. I can also see, looking at the QQ plot, that the majority of the data, again, except for the outlier, are very close to the line. Additionally, the Box-Young test says that the data is not autocorrelated, and the ACF plot indicates that there are no significant lags. I'm comfortable using the ARIMA model to forecast, however, I'm not confident in that decision at this stage and could consider cubic seasonal model mentioned earlier. That being said, I am sticking with the ARIMA 011 model to forecast the time series for the time being. My forecasting occurs immediately after the probable change point and predicts the iron ore price over each of the next 10 months to be around $144 US per metric ton. The 80% and 95% confidence intervals are provided. The 80% interval indicates that the iron ore costs will be between $131 and $157, whilst the 95% interval forecasts that the price will be between $124 and $164 in September 2021. Thank you for watching.